Hi guys, hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In my channel, I deal with different subjects ranging from mathematics, physics, chemistry, and biology, and also related topics. So today we're going to look at the concept of integrals, and this basically is an aspect of integrals whereby we are going to look at different functions and try to do a comparison. So this is going to assist us in any case if there are some conditions which have been attached to functions, then we can be able to evaluate them appropriately. So therefore, I'm going to use an illustrative graph on the board, which is going to assist us, of course, try to achieve this, that. So therefore, I'm going to have this two Cartesian coordinate system of two axes for x and y. And from this, of course, if we try to give perhaps a graph of y is equivalent to x, we can be able to illustrate this one. Perhaps I use a different set of graph. So this is going to assist us try to interpret the specific concept of comparing functions for this specific discussion. So if we have a graph of yx, which is given has been marked as such, or given a scale as such, so this is 1, 2, 3, 4, 5. This is 1, 2, 3, 4. So we're going to have this specific marks for x and y axis given that specific point. So if we are trying to draw a plot of a graph of y is equivalent to x, then the value of 1, 2, 3, 4. So we shall have a plot of this straight line that is running through the origin given as such. So we're going to have this specific function whereby y is equivalent to x given as such. So there are various ways in which you can be able to give this specific notation for other functions, and especially for graphs, as we said, we can be able to give a general representation for y is equivalent to f of x given as such for different values of this specific value for x. So in this specific respect, then therefore I'm going to have two functions represented as such, whereby we can be able to have a function which is just given as such, which is a curve, and this is going to represent f of x, or y is equals f of x represented as such. And suppose I have another function which is given as y is equivalent to g of x given as such. We can be able to allocate or rather try to observe different characteristics for this, especially in terms of the quantity or the extent to which they are being placed from the origin. From this particular point that I've given as O, which is basically, or 0, which is basically going to be the origin. So in this case, I can be able to observe that the function y is equivalent to f of x is greater than 0 in this specific respect, and therefore with regard to this one as well, the graph g of x is also greater than 0, bearing in mind that if we have a function at this specific point marked 1, 2, and we proceed upwards along the positive y direction, I can be able to draw a line at this specific point and then write this one, y is equivalent to 1, giving it that specific value, numerical value, and this is y is equivalent to 2. So at a particular point, then therefore along the positive y-axis, then therefore I can be able to have those two graphs represented as such. So in terms of comparison, then therefore we can be able to give these two graphs, whereby the graph of y is equivalent to f of x is going to be greater than the graph of y is equivalent to g of x. Then therefore we can be able to make a conclusion and say that f of x then therefore is greater than g of x given as such. So if you try to look at similar graphs with the one that I've given on the board, or maybe try to do a comparison of two graphs, we have already looked at the concept of integrable graphs, and also the derivatives of graphs at a closed interval in some of our video. So therefore, as I've said, of course, we have been able to determine how we can be able, or rather we have been able to determine the integral and the derivatives of various functions from our previous discussion. And therefore, I can be able to give a notation for the function f of x, on closed intervals, perhaps a, b, given as such, and then g of x. So this y is equivalent to f of x and g of x at closed intervals a and b. So these ones are the intervals along the x-axis. So therefore, if I am going to have my point given as a at this specific point, and b, we said that the integral of this specific graphs for y of x at g of x is going to represent the area of the bounded by the curve and the x-axis. So this is the lower part. Let me demarcate it as a1, and therefore the graph of y is equivalent to f of x. Sorry for that. Can be given an area that is going to encompass this first and second one, which is of course can be able to give us area 2, whereby area 2 is equivalent to the area bounded by the graph the x-axis, and y is equals f of x given as such. So this therefore still implies that the function f of x is greater than g of x given as such. So therefore we can be able to make a conclusion that the end line of a curve that is passing on the positive axis, y-axis of this specific line, or rather the x-axis, then therefore it's going to have a function, as we said, f of x, which is greater than or equivalent to 0. So this is generally, it can be 0 or greater than 0 so long as it's going to lie along the positive x-axis. So for every point in this specific interval along the x-axis AB, we're going to see that we can be able to give an integral from a to b of a function f of x given as such, dx, which can be greater than or equivalent to 0. So this is a representation for an integral of a function of f of x from a to b, which encompasses area 1 and 2, which can be able to be given as such. So similarly, we can be able to give the integral of a function from a to b, g of x, also greater than or equivalent to 0, given as such. So if we try to compare the two graphs for this one and this one, as we said that of course f of x is going to be greater than g of x, we can also be able to give the comparison for the integrals of f of x and g of x by giving this specific comparison whereby the integral of a to b f of x dx is greater than or equivalent to the integral of a to b g of x dx given as such. So this is how we can be able to compare the graphs of two functions. And in any case, if we want to find the difference between, or rather the area between, or perhaps if I can say area A2, then therefore we're going to find the difference between the whole area for this graph that is f of x bounded by the x-axis and this one, and then we minus the area below this one, and then therefore we will be able to evaluate that. So so therefore this is going to give us a sense in which we can be able to do a comparison for various graphs, and this is going to assist us evaluate various areas bounded by the graphs, or rather two graphs, in case we come across them in some of our discussions. So for now, I'd like to request our members to kindly go to the description box of this specific video. Check under the playlist. We are going to have a link of a particular link of videos which are going to be especially on integral and the differential calculus, which are going to assist us, of course, understand better on some of the characteristics of our integrals. So for this case, I hope that we are going to do a proper comparison in case we come across various graphs, and a comparison between two graphs. Of course, these are some of the laws which are going to be applicable, and they're trying to allocate some boundaries for the closed intervals as we have done. So that is it for now, guys. Bye, God bless.